3, 2, 1, go. We're live. This is Retrace segment number 78 for Sunday, December 11th, 2022 at 11 p.m. Eastern, 8 p.m. Pacific. Retrace is about what's going on out there. The short answer to that is computer control. The long answer to that is not happening right now. Mathematical disclaimer. I should not be your mathematician. Artificial intelligence disclaimer. No, I can do that. I can be your artificial intelligence interpreter. I feel like I'm building that skill set. What are we doing? We're doing a recap of the gradients and partial derivatives in the context of AIMA4e pages 119 to 122. We're in the December to Remember Math and Code event in preparation for our deep dive study of AIMA4e, Artificial Intelligence, A Modern Approach, Russell and Norvig 4th edition. We're going to start that in January, that deep dive. December to Remember is about math and code. We are looking for math and code that might get us. Get you. Pinch you with the pinchers, the summation notation pinchers or the like. This math is going to sort of hook you like a fish hook, that backwards D, or that fancified D, not backwards, the partial derivative. All right. So, what's the problem? I'm going to explain the problem to you. First of all, let's have a look at just a visual here. That's sort of what you might be. You could put that in your mind, right? This is picturesque. This is beautiful. What are we talking? Why are we looking at that? Okay, what we're doing, the problem, the toy problem, and we're going to do a toy version of the problem to really solve it so we don't waste a bunch of time doing calculations that don't prove anything and don't teach us anything. We're going to do a toy version of the toy problem, but the toy problem provided by Russell and Norvig is the Romanian airport location problem. Bunch of cities in Romania. You want to place 3 airports at the best location to make all the citizens of those cities and of Romania more generally. Why not all of them? Not just the city dwellers, not just the city mice, but the country mice. We want to place the locations of those airports such that people are happy. What does the map look like? Let me see if I can pull it up quickly here. Is the map on this? Well, here we go. Let's look at this. This is our map of Romanian cities, and later on we're going to pick Făgăraș and Bucharesti as our first 2 cities to do our toy version of the problem. But when you picture the Romanian cities, picture that map. All right. Why is this an interesting problem? Well, if you're going to place 3, it looks like maybe you can just sort of eyeball it, but you can't eyeball it. It's hard, and you need to do math, you need to do algebra and calculus, and you really want your machine to do that stuff, but you're not going to understand it if you just do pip install solution. Okay, you don't want some. You got to do the toy version so that when you do use the software, you know what you're doing. Okay, let's go to our first notes for Re70. This is a recap, by the way, of Re70 through Re76, if I didn't say that already. Okay, so here are the notes for Re70. We have a 6-dimensional solution space. What does that mean? It means that there are 6 different numbers that we can change to improve our answer. And when we talk about improving our answer, what we're talking about is we have to have some sort of objective way of scoring our guess at the locations of the airports. Okay, so if we listen, I feel like someone is landing a Romanian airplane right near us right now. Is that loud to you? It's loud to me. We're going to place, we can guess on the map, like just drop 3 pins and, okay, are those good? I don't know. You can measure the straight line distances to each of the cities. You can do something even better, measure the square of the straight line distances. But so what? Let's say you measure something and you say, okay, they're this far. Our 3 pins are this much far from each of the cities. Is that good or bad? How do you know? Well, you can say, let's add up all those numbers and get them lower. But what if the behavior of that sum doesn't produce what you want? What if you have situations where an airport could be right next to a bunch of cities or some of the cities and really far from the other ones, and the sum is the same because you move it here, you move it there, and you get the same score? Then what? Here's the solution. You need an objective function that takes into account something other than, oh geez, I didn't do the objective function until Re73. Okay, let me just finish that thought, and then I'm gonna do an apologia, an apology. Okay, here's our objective function. This is how we're gonna score our little guesses. Okay, it looks kind of crazy, but we'll get to it in a second. We said at some point in one of these notes, in one of these segments, and by we I mean me, that von Neumann said it, so we can say it because von Neumann said it. Nobody understands mathematics. In mathematics, you don't understand things, you just get used to them. I think that's a good way of thinking about this problem. We're going to make several layering passes. If you listen to all the segments, we're going to layer our understanding over the problem by passing over it several times. The first time I went at it, I thought I could explain it. I understood in my mind the pictures and the math, corresponds to the pictures. But then when I tried to sort of, verbalize it or articulate it, I kind of fell short. So that was our first pass. It's kind of fun to listen to. You can go have fun with that one. But what we're going to do in these notes and in the segments themselves is make several passes at understanding this. It's not really, it might, if you find it easy to understand in this short version, then you might find the other ones sort of repetitive or redundant or unnecessary. But I don't think most people will find it that way. Not most outsiders, and Retraice is for outsiders. Okay, this is our first guess, or this is the algebra of a guess of 3 airport locations. X1, Y1 is the first airport, X2, Y2 is the second airport, X3, Y3 is the third airport. We can represent that as a vector X, and the F of X is the score of this guess, okay? So we drop 3 pins on the map, we do some fancy pants mathematics here, and we'll explain that in a second. And then we get a score, and then we can compare X sub 1, our first guess, to X sub 2, our second guess, and that is going to look like, wait for it, this, okay? Okay, we'll get to that in just a second. Okay, why does our objective function, why does our scoring equation, don't look at that, look at me. Why does our scoring equation take the sum of squares? It's absolutely the problem of zero-sum movement of the airports. Pretend each end of this line is a city. We only have 2 cities, and we're going to place 1 airport. Score here, if we just add the distances, is 20. Sum of distances, score is 20. Let's move that airport way over here to these lucky people, and screw these people over here. Score is still 20. That can't be good. Our score can't fail to reflect an airport that's way better for this city, way better for Bucharesti, and way worse for Făgăraș, okay? That's why we use sum of squares. Here's what happens with sum of squares. You move your airport away from Făgăraș and toward Bucharesti, and your score goes up. We are trying to minimize this score. You could multiply it by -1 if you prefer to increase scores. But you'd still be working with negatives, but you could do whatever you want to the final arithmetic there to adjust it to your liking. But we're doing gradient descent. We want to descend this score to the lowest possible. You can think of it as a cost. Oftentimes in gradient descent, most times you're thinking of a cost function. You want to minimize the cost. So the lower our score, the lower our cost, the lower our unhappiness of the Făgărașis and the Bucarestis, the better. Okay, so we use sum of squares because the sum of the squares of 15 and 25 are 250, but the sum of the squares of these are 200. 10 and 10 are 200, and there's no difference in the sum of distances. Got it? Here's our gradient. This is the whole thing that attracted us to this particular problem. We have a fancy symbol here. We have fancy symbols throughout here, and it's lots of them, not just a few. This gradient of f, it's called an operator, and it doesn't say, there's no subscript here, but there really should be a subscript that says x sub 1, because this is the gradient of f of this first guess. These 3 airports are part of this guess. So it's not the absolute gradient of f. It's not the absolute total derivative of all these partial derivatives of f. It is of a particular guess that we have to plug in here to find the value of this gradient, which will end up being basically like a slope. Okay, so we have to talk about this, how to think about a gradient. So you understand what a slope is. It's like if you're on a hill and you're standing here, there's a tangent line on that hill that represents the slope at that moment. You move down the hill, the slope changes. It gets steeper. You move up the hill, it gets less steep. You're at the top, there's no slope at all. Okay, your slope is 0. Go the other side, slope is correspondingly changes to the curve of the thing. Now, what if you do that in 2 dimensions? You're on a hill, okay? If you stand here, your slope with respect to the x-axis is this, but with respect to a perpendicular axis is this, okay? They're not necessarily the same slope. If you're standing here, slice this into 2 planes, let's say, to achieve our perpendicular axes. If you're standing here, going down this way is not as steep as going down this way, okay? So this is the partial, so any slope along this axis is a partial derivative, and any slope along this axis is a partial derivative, because we're in 2 dimensions here. And together, you put them together, and the slopiness at that point that takes into account both slopiness in this direction and slopiness in this direction is the total derivative. Okay, that's what a gradient is, except you're not in a 3-dimensional space where you've got these two axes and you're up and down. You're in a 6-dimensional space, and it has nothing to do with land. It has nothing to do with Romania or airports. These are different numbers, different values when we calculate these slopes. Okay, so we have to calculate a slope of the function. How slopey is it with respect to the x1 axis, i.e., where we can put the x coordinate of the first airport? How slopey is it? And this, again, the slopiness represents, like, going up and going down in our little hill model here is increasing or decreasing the objective function value. So what we want to do is go down, wherever we place our first guess, we want to go down to the nearest valley, and this only works to the nearest valley. You can't find a valley that's several hills away. You need other techniques for that are not that complicated, but we're only going to find a local minimum, not a global minimum. So we want to go as fast as we can to the center of the valley. You can, if the center of the nearest valley is right here, there's a little flag, little golf flag here that tells you exactly where the lowest point in the whole neighborhood is. You can get there by going like this, the long way, but that's not, you want to go straight there. The gradient tells you, with all 6 or however many partial derivatives you have, all partial slopes together, what the precise direction is to go from where you are to most quickly improve your function score, your altitude, your elevation, and most quickly to descend down this hill, however many dimensions you're in. And I know it's kind of hard to think about 6-dimensional space, but it's basically the same thing mathematically. It's hard. You can't picture it above 3-dimensional space, but you can do the math the same way you do on 3. You do it on 6, and that's what you have to do for 3 airports with 2 coordinates each. You want to go as fast as you can toward that score down here. That's what gradient descent makes it possible to do. There's some qualifications to that. How many steps you take before checking your function value again, checking your elevation again, makes a big difference. If you take one giant step and you're jumping, your legs are long enough to jump over the local minimum, then you've overshot the highest local value of the best local value of your objective function. So you got to take steps, but if you take too many small steps, it's going to take you forever to get there. That's the problem with step size. We'll look at step size in a second here. But just picture a 6-dimensional hill or an n-dimensional. You can do 5,000 economic dimensions. You can do anything when you're dealing with higher dimensional mathematics, as long as you don't insist on being able to picture that hill as being anything other than a hill. If you really insist, you can picture things like changing the color of your point or changing the fuzziness. But that's too much in the weeds, okay? So the slopiness is these 6 things, these 6 angles on the slope, let's say, and it's of our objective function at this point, this vector point, our first guess, and it tells us, once we have this, how much to move in each direction, as a ratio, or as one big slope. In order to improve. And then the only question is, how many steps do we take? Here, I just made some notes about struggling with articulating what I just articulated. Okay, that's Re70. Now that we're going to go over these things a few more times. Again, the toy problem, we've already talked about this. Pile of numbers, we've talked about in previous Retraice segments about reducing our hypotheses to a pile of numbers. And that's what we're seeing here. We're seeing a vector in the form of our... I clicked it, didn't I? Didn't I click it? Oh, man. Where's my? There it is. In the form of our first guess, our first 6-dimensional guess. That's a pile of numbers. Hypotheses are sort of like guesses. Piles of numbers. Go back and look at Retraice hypotheses 1 through 11 or 1 through 12. Okay. The gradient equation again. Here we elaborate some of what I just said, if you really want to go into it, and this also represents the point at which I didn't quite know how the gradient was going to tell us which direction to go. It wasn't until I worked through this that I realized that it was basically like a slope, and the only question was how big do you want to take your step? But the slope tells you the rate at which to take your step, which is the direction. Give some more footnotes down here. Retrace 72. We really break out the equations. This is our guess again. This is our function of a guess, which is our score. This is the gradient we just talked about, and this magic little gem here that we saw in the footnote of Retraice 71. This is the algebraic definition, the limit-based. You can define this using infinitesimals, but everyone uses limits these days, although there's a little bit of controversy about that, but not much. A limit is just sort of a logical mathematical object that says, what if we take this, we put an unknown or a variable into an algebraic expression and keep recalculating it closer and closer to zero. We never quite get to zero, because if we put zero under here, it's going to be undefined, or zero just here, and it's just going to end up being the same as f of x. But if we put it in there and keep going and going, can we get the slope just by sort of logically following the trend of the results of this calculation, instead of actually being able to calculate an infinitesimally small slope? And that's what a limit does. And each one of these partial derivatives is defined by an algebraic limit. What do they look like individually? They look like this, okay? So to calculate them, if you want to get out of fancy, fancy D and these symbols that are sort of hard to understand. Here comes another plane trying to land in Romania. We haven't placed the airport, and this plane keeps flying around outside trying to land in Romania. This isn't Romania. I don't know what this guy thinks. Man, there are too many people watching this. Everybody's too focused on our work here. Okay. So each one of the six needs its own little version of the limit equation, and you need to vary only the variable that you're measuring the slope with respect to. So for the first one, we add the h. The h is always in the denominator. We always subtract the normal calculation of the objective function over here, so we can only focus on the difference that's calculated here, and then we vary the variable, the independent variable that we care about right here. So here we do the first one, then the second, then the third, and you just add the h to each one and keep the other five stuck still in place so that they're not changing. So you're only measuring the slope with respect to each dimension. So that's how you expand it out. And then we go over to Retraice 74, where we actually place some cities on a map, or pick some cities on the map, and then we start measuring distances, because in order to calculate the objective function, we're going to have to do some, it's not really trigonometry, it's Cartesian geometry, let's say. So we picked some nice round numbers. This is going to come back to haunt us in a minute here. And we calculated the distance between Făgăraș and Bucharesti. We didn't really need to do that. We need to calculate the distance between Făgăraș and Bucharesti and an airport, but we didn't want to place the airport here yet. So we were just doing the math on a very simple triangle, because we're going to have to do it on several more complicated triangles later, or at least more triangles later. Here's the math calculating the distance. This is just basic algebra based on the Pythagorean theorem. C squared equals a squared plus b squared. Don't go too far. If you only care about the square of the hypotenuse is the long side over here. If you only care about the square, don't accidentally start calculating the actual length of the hypotenuse, because it's not what you care about. You only care about the square. Who cares, right? To forget one's purpose is the commonest form of stupidity. They say Nietzsche said that. I don't think he said it. I can't find it in any of his books. No one else can either. Everybody puts it in memes, but they can't, no one ever. People say it's in certain books. It's not in those books. I checked those books. It's pretty easy to do in an evening if you have half an hour of time available to you, and I couldn't find it. Okay. And I said some things that, corrected in the footnotes. Here's the calculating the objective function. So we start with the abbreviated form of saying the objective function, expand it out, put the variables in there instead of this representation of the vector. This is our pile of numbers. This is just the algebra. We are not using specific numbers. Then we need to add together each of these, for one of these things for each airport. So we have 1 airport to 3 airports, and we're going to do the math on every city that's closest to each of those airports. So this is the set of cities closest to the ith airport. So we'll do one of these for the first airport, then one of these for the second, and then the third. And all we're doing is adding the sum of the squares of the distances between those cities, and they are represented by subtracting the x and the x coordinates one from the other, and then the y coordinates one from the other. One from the city and one from the airport, or one from the city and one from the airport here. It doesn't matter what order you do them, because you're going to square them, blah, blah, blah. Okay, that's Retraice 74. Retraice 75. Oh, bang, we finally placed an airport. Can we please just place an airport? It's taking too long. Okay, did it. Placed an airport. Man, did I pick the wrong place to put that airport. I wanted to put it someplace that wasn't perfectly centered, but the gradient descent was going to help us put it where it needed to be. But man, I caused myself some grief. Okay, Făgăraș coordinates are 14, 13. Bucharesti coordinates are 19, 6. Airport guess number 1, x sub 1, vector x sub 1, 1811, and then the set of cities whose closest airport is x sub 1 is c sub x sub 1, and that's just c fa and c boo. Okay, let's see what it looks like. This is what it takes just to calculate the objective function on that first guess with just 2 cities and 1 airport. Go through the algebra if you like. This explains it to some extent. During the live stream, I said this is supposed to be blue. I was right in my notes and wrong in my live stream. It's not supposed to be blue because that Y comes from here. It's not blue yet until we do something else. Okay. That's not an airplane that keeps flying by. It's a shoveling truck because it's snowing outside. I figured it out. I figured we got to take a moment here. We were panicking in the studio. I have people working on this. I'm being told that is not a bomb dropping fighter jet from the Romanians who have lost patience with us. It's a snow shovel truck. Okay, if you can hear that in the background. I know you can't because on podcasts, the podcaster can always hear everything and you can't. But trust me, it sounded like we were being bombed. It still does. Okay, I'm not comfortable at the moment. Calculate the objective function for an airport guess of 1811 and you get 46. That's our score, okay? And you go down and you can read the citations. Oh, geez, God, it scares me every time I see it. Okay, Retraice segment number 76. First airport guess. Second airport guess, so first airport has its score here and faded, 46. Second airport guess, 1710. How did we get to the second one? Gradient descent, man. We did gradient descent. We're not guessing. There's not guessing anymore. Now the mathematics is taking us where we want to go. So I had to do this scribble by hand math, and it's I kind of like it. It's fun. It's fun to look at, right? So our first guess, this is the math. Some of the stuff I had to throw away. Our second guess starts here. State is, and I put a bar over it because bold in writing does not signify a vector because I use bold for other things. So I put x bar, but it's the same as just the bold x in LaTeX or in the fancy notes. This is our guess number 2, which corresponds to our second airport location guess, 1710. Okay, so we calculate that down here. We get a 38 for our objective function. Better than before. I like it. But then we start to get nervous. Actually, it started with our first guess. The polynomial that describes the parabola, it's a 2-degree polynomial, so it's a parabola, it's positive. It'd be positive by the way, was the same for both our, where can I show this? For our partial derivative of f with respect to x sub a, the first dimension, and with respect to y sub a, the other coordinate, the second dimension of the airport, they were the same. I'm going to explain why in a second here. But I kept going with it, and I looked for problems with my math, couldn't find them. Same thing again, polynomials the same for both. It's different now. The second term is a little bit smaller, and the objective function, this c, this constant over here is smaller. So, I'm getting less nervous at this point. Then we do a gradient descent again. So the gradient that we got, how do we get it? Okay, so what do I mean when I say we're doing gradient descent? So on the first guess, so the partial derivative of f with respect to x sub airport at state x sub 1 or x bar sub 1 is this. I'm just doing the calculating the derivative in a spreadsheet here. No cheating. This is all just simple arithmetic. But what we're doing is several iterations. We're making h smaller and smaller and smaller, tending towards 0. Okay, every one of these h's is smaller, and then calculating the polynomial that describes f of x plus h comma y, in this case 18 plus h comma 11, to get the total of our function value with h in it, and it's trending toward 46. You can see here trending toward 46, okay? But it's not getting to 46, and this part that's left over is the part that we care about, okay? You subtract 46, and you get the part that you care about. It's getting closer and closer to 0. This rate that we're getting is closer and closer to 0, but we don't know what the rate is until we divide by h. So we put this under this total, and then you get whatever's left over, and it's 6. Okay, it's trending towards 6. The partial derivative of f with respect to x sub a is 6 in the limit. Now, it's not 6 like you could just do the math. It's a mathematical logic conclusion. So it's a logical argument that says this number is going to keep going, just as h keeps going, because we keep dividing by 2. this number, as we do that, as we calculate it in the context of this other function, is going to keep, or as the result of this other function, it's going to keep trending toward a number itself. And that number is 6. Never going to get there, but we define the result of this sequence as the number that it will get to if it goes on for infinity. It's calculus. I know it's kind of hard to get used to, but you get used to math. You don't have to understand things in the limit. You have to get used to them. You have to understand what people mean when they say something's in the limit. Okay, that's what they're talking about, the end of that sequence, that forever. We don't do it forever. We do it about 20 times, and we become convinced about this point that this in the limit is going to be 6. Okay, and we didn't have to do it for the second airport guess because we knew that it was just going to be the same rate, right? Yeah, because I did how did I convince myself of that? So the rate with the other polynomial is this. You subtract that, and we're going to end up with, well, yeah, because it's going to be the same thing over the same thing, and we're not changing directions. We're only in 2 dimensions, so the direction's going to stay the same. So the rate's going to stay the same. Okay. Is that true? I don't know if, come on, I didn't calculate the second rate. What was the second rate? I know I was heading in the right direction, but I could have calculated the second rate. On what basis? I can't remember how I decided that I didn't have to do that, but I decided I didn't have to do it. And I went in the same direction. And how did I pick my next step? I went half the distance. So it's choosing the step size for this last one. I went half the distance to here. Gosh, I was all steeped in it, but now I didn't write down every single thing, every single thought. In the same direction. The key is that I couldn't go a full step. I would have overshot, so I said half the distance, and it turns out that half is spot on. My step size. What I'm saying, it's not. I'm not. The math isn't wrong, but would the slope have been different? Maybe it would have been different, but it doesn't. It still would have been the direction, because we're only dealing with 2 cities. The direction would have been the same. So the slope doesn't really matter as long as we know that the slope is in the same direction, and it is. Okay, and the choosing a step size of half. I can't remember if I had perfect grounds for doing that or if I just chose it. But choosing step sizes, you never have perfect grounds. There are different arguments for choosing different step sizes. So that's all I'm hesitating about there. Anyway, the next step size landed us perfectly on 16.5, 9.5. And it also lines up with, if you just do the geometry of this, we know where this point is supposed to be. So our common sense agrees with our gradient descent. Score is 37. 37 is actually the perfect score. It is half the square root, or half the square of this distance. The square of this distance is 74, as we calculated in the previous segment. Half of that is 37. So our gradient descent looks good. The last thing to make sure that we're doing this correctly is that this final slope that we calculate, the d of f with respect to x sub a for the third guess for state x sub 3, or x bar sub 3, needs to be 0. If we've really reached the bottom of our gradient, we've reached the local minimum, then the slope down there should be flat. There should be no slope. Our slope with f of the partial derivative of f with respect to x sub guess 3 and with respect to y sub guess 3 should be 0. If that hadn't been 0, I would have doubted what I would have thought I made a mistake. It was 0. It tends towards 0 down here in the limit, as partial derivatives always do, okay? And down here, and at the end of the segment, last segment 76, we talked about how you can do gradient descent using tools that are already built, software tools that are already built. In particular, this 6-line, 7-line function. Gradient descent. Take the gradient, take the start, the learn rate, and the number of iterations. And okay, anyway, that's the easy way to do it. But you're not going to understand what you're doing if you do that. Which, in life, you got to do a lot of things you don't understand. That's it. Okay, so that's what we did. That's the shortish version. The details are in the notes. The details are in the original segments. This has been Retrace segment number 78. And same time tomorrow, 11 p.m. We're not doing a doubleheader tomorrow, I don't think. So 11 p.m. Eastern, 8 p.m. Pacific. All the notes for today, and all these notes are at retraice.com, retraice.com, AIMA4e.retraice.com for our companion to AIMA4e. links.retrace.com to get to all the other sources that we use, and notes.retrace.com to get to our notes. All right, signing off.